All right, let's get started. So welcome back. I apologize. I had uploaded the wrong one, which has some transformer stuff on it. That's not going to be on this test. We already did that in last test, right? So we don't have to cover that again. So it should be a little less material. It's still the same stuff, but just less transformer stuff. So I apologize for any mix-up or confusion. So this is the updated file. I just uploaded the wrong one, so I apologize. So we'll go through the whatever questions you have, or we can go through this material and kind of give you some key things to focus and point or learn about, think about. But we will say, because I've had a number of people stop by with homework questions on this, it's all, you got to be able to do AC circuit analysis. You got to be able to do three-phase power, power triangles, understanding what reactive power is. All that stuff that we did at the beginning of the semester is still applicable. So you need to make sure that if you're struggling with any of those concepts, when to use the square root of 3 or when to use 3, when to, do leading or lagging, that type of stuff, all that stuff is particularly important. And I say this because over the week right before break, they brought in some ECE candidates because they're hiring a position for power. And one of the candidates they brought in, she was doing her presentation and she mentioned a lagging power factor. And then when she did her S calculation, she came up with S first and she wrote a positive angle. And when somebody said, hey, that's a lagging power factor, why does S have a positive angle? She couldn't explain. This is somebody with a PhD, and is looking for a job. She couldn't explain the concept of leading or lagging. So it's not to put her down or to put you down. It's just a topic that if you don't think about it and understand it, it can cause a lot of problems. So make sure going into the test, you go back to those fundamentals: AC circuit analysis, three-phase power, power triangles, leading and lagging, power factor, because we're just going to keep building. And if you take the follow-on class of this class, again, we're just doing more and more building on that material. So I equate this class kind of like electronics. In 241 and 240 or 342 and ECE, it's 342 and 343. You have to do AC or DC circuit analysis to be able to apply and learn some of the concepts there. But you just expect, or they expect you to know DC circuit analysis to be able to do that material. It's the same thing here. You have to be relatively competent in doing AC circuit analysis to be able to understand the material in these two courses. Okay, so feel free to interrupt and ask questions about any of the material, and we'll go from there. So this is the first time that we talked about rotating something, rotating a machine. So we do have phasors, voltages and currents, that their phasors rotate, right? That's the sine wave, but we always do things in steady state. So in AC circuit analysis, we assume that the rotation is non-existent, even though it is actually happening. We don't need it to do any of the calculations. And so we do snapshots in time, and then we do things from a consistent steady state standpoint. Over here, we actually take advantage of the fact that we have those alternating currents, primarily the currents, to go ahead and create magnetic fields that are alternating as well. And so it's really important to understand how you get magnetic fields that rotate, because that's how the concept of machines will operate. Okay, a machine wouldn't be very good if it was not permitted to rotate. So we looked at the concept of a stator winding. That's where we started off this discussion about how we get these rotating fields. And we just looked at the stator winding. So the stator winding was just physically stationary. We had 3 windings because we're talking about three-phase machines. And we used 3 windings. And the first ones we looked at where they were mechanically spaced 120 degrees apart. Remember, a winding has an in and an out. So the ends were all 120 degrees out of phase from one another. And when we did that, when we did those calculations, we saw how we could get magnetic fields using essentially our modified right-hand rule. Current going in, wraps around in the winding, and our thumb gives us that perpendicular direction or perpendicular plane or perpendicular direction to the plane of where our current will be going through. And then we get a corresponding magnetic field. And we did that for all 3 phases. And then once we knew what those would give us for positive current going in, we could add those vectorially to end up with a net magnetic field. So all those magnetic fields inside the machine are going to add together to create one magnetic field. So when we applied a set of balanced 3-phase currents to those machines, again, those are same magnitude, offset by 120 degrees. we saw that we got nice, smooth rotation of our magnetic field, whose magnitude was always 1.5 times the magnitude for any magnetic field produced from one phase. It didn't matter where you were. It was always 1.5 times that value. And it rotated at the same speed as, well, I shouldn't say same speed, but you could calculate it. It was proportional to the electrical frequency of the system. So that's when I say same speed, it was proportional to the electrical frequency. So we actually got this nice magnetic field, which, remember, when we talk about magnets, if we have two magnetic fields interacting, we can take advantage of those to actually cause something to rotate. So the concept of electrical machines is we just get this magnetic field rotating around and we're going to chase it. And the speed of rotation was determined by the number of magnetic poles, not the number of wires, because we already start out with 3 wires, but the number of poles is we're going to end up having a second set. Here's a key thing, a second set of windings, so that now we can get another magnetic field that originates inside there. Okay. And so the concept is we now have 2 magnetic fields with 2 sets of windings that are going to rotate around, and mechanically we only have to rotate half the distance to get back to where we're starting out back with the north and the south. So by dividing that motor or that stator into magnetic halves, if you will, you actually could adjust the speed of operation. You don't need to operate at that same speed because you have that second winding that comes in. So you're basically getting back to the north and the south. And again, magnets always try to line up. So if you have one spinning here and another one spinning here, it only has to spin at half the rate. So then we ended up expanding that to come up with this really simple relationship, which is the electrical speed is determined by, or I shouldn't say the electrical speed, because the electrical speed is the frequency. But we can get either the mechanical speed or the electrical speed just by multiplying the mechanical speed by the number of pole pairs. So each set of windings produce 1 pole pair. So if you wanted a 2-pole machine, that's considered a pole pair machine. So it's 1 pole pair. So you need 1 set of windings. If I wanted 2 pole pairs, that means I need 4 poles. So that would mean that I need 2 sets of windings, and on and on and on and on and on. But what we see here, yes, sir, go ahead.
When you say set of windings, is that all 3?
All 3.
So you need like 6
You need
windings per 2.
You need 6 sets of windings, yep, or 12 wires, right? And in and out counts for that. So yes, we're talking about 3-phase machines. We want to make sure that we have a balanced load as much as possible. So we're going to put 3 windings or a set of 3 windings every time we're adding a pole pair. We're not going to add 2. Now, theoretically, if you were being on the cheap and you wanted to go ahead and do that, you could probably do that, but that motor is not going to last very long, because the whole advantage of having 3-phase is you get that 1.5 B sub M. If you have 2 phases, you don't always have the 1.5 B sub M. It's going to vary up and down all over the place. So you're going to have a motor that vibrates. It's not going to be consistent torque. Either the motor is going to get damaged or the pump is going to get damaged. It's not something you want to do. All right. So that's why when you buy motors, again, anything most likely above 10, maybe 15 horsepower is almost guaranteed to be a 3-phase motor, just because other motors just don't last that long. Okay. Now you have some unique applications and whatnot, like we talked about conveyor systems, where you might have, a DC motor or something like that. And then in your house, you do have some single-phase motors, because why? Why do you have single-phase motors in your house? You don't have 3-phase in your house. It's very expensive to run 3-phase to the customer. Right now, to run to your house, the utility basically has to run 1 wire to the outside your house. They run 2 wires. Actually, they technically run 3 wires in your house, but they only need 1 wire. And then the return path of that wire is ground. They can actually use ground to return the current. It's okay if you use ground as a return path, even if there's current flowing through it. I'm standing here. How much current's going to go through me? I'm standing on ground, so I'm at 0 volts. Why would any current go through me, the individual, if it can use ground, which has a way lower path of resistance? So you can use ground as your return path conductor, and we often do. We do that a lot because everywhere you look, right? There's ground pass, and the electrons will flow in any way they can. And normally people think they flow along the surface. Most of the time they flow down. Anybody want to guess as to why electrons flow down before they head back? They're looking for the most electrically conductive point. Where do you think you're going to find the most electrically conductive point? Where it's moist and wet, right? So the deeper you go, there usually is a more consistent level of water. It's, if you're in the desert, it's different. But if you're deeper, you can go down. So that's why sometimes you'll see people drill wells. They literally drill wells, not to access water to drink, but to access water for an electrical conductivity location. So you can go depth and you can get into the water table, and then you can have electrons flowing through that way. And again, everything's at 0 volts, so you're not worried about electrocuting things or anything like that. So the simple relationship is the number of pole pairs, right? P divided by 2 is the number of pole pairs. You multiply that by your mechanical speed, and that's how you get your electrical quote unquote speed, which another way we say in electrical engineering, we call that frequency, right? Radian frequency as opposed to speed. So electrical engineers talk about speed, but it's just a different representation because we don't actually see physical rotation unless you're looking at an oscilloscope. All right, so that's the first one about AC machines, but we really didn't even care, if you remember, how the rotor was configured. We hadn't even introduced the concept of a synchronous machine as of yet, so we were not interested in focus on that. Then we're going to look now at losses in machines. So this is helpful if you can understand where your losses in a machine go, then you can actually have a pretty good indicator of calculating efficiency. And we as electrical engineers, we have two concerns, because if the generator is the power output, we need to know exactly how much power is being supplied by the grid. If we're the motor, we need to know how much power that motor needs, including reactive power, so that we can size the cables and all that stuff to do that. So for an electric motor, we can see that the input power is electric and the output power is torque, right? Or a multiplication of torque. And then we start dropping power. And we drop power based on which quote unquote domain we live in. I consider this electrical domain. So this is I squared R. So it's not torque, it's actually heat. Over here, we are still in electrical world. We're losing power in the magnetic core. So we haven't converted anything to a torque yet. We're getting close, but we're having there. So this power over here converts from the stator to the rotor. Over here, this would almost be like a developed power, which is the torque that we have. That's developed torque. Once we get beyond this point, all the losses we would consider are what we consider some sort of a mechanical loss. And then when we end up with is our output torque. Opposite for a generator. So in a generator, and again, when we say, and you hear this all the time if you're reading articles on utility stuff or watching the news, the generator generates electricity. It doesn't generate anything, right? So it's an unfortunate use of the term. But really a better way to say it would be a converter, because a generator really converts mechanical energy to electrical energy. Same thing as a motor. A motor converts electrical energy to mechanical energy. So that's really what these devices do. So if you use the term converter, it would apply to both. You could be a motor or a generator, which these can do. But over here, we're applying a torque. And that torque is from a steam turbine, gas turbine, reciprocating engine, hydroelectric facility, could be wind, probably wouldn't be solar. Why wouldn't it be solar? Could it be solar? Yes, sir. Yeah, it's not rotating, right? There's no rotation. And usually our mechanical engineering friends say, hey, once we get into the mechanical world, we start getting really losses in efficiency because we have something rotating, which means we've got problems and you're losing efficiency. But anybody have a guess as to what like the maximum efficiency of a current state-of-the-art solar cell is? Yeah, 25% would be like really, if you could get a solar cell that would be 25% efficient, that's pretty impressive. So compare that to a pretty decent, not an amazing, but a pretty decent steam cycle system, just a steam cycle only. And you're talking 33% efficient conversion from chemical energy to electrical energy. Because remember, that's a steam turbine. It doesn't just have mechanical. There had to be a chemical process that was put into it, like natural gas. That's a chemical process where you convert natural gas and you convert the energy in natural gas to heat. What do? You burn it, right? And then there's a heat process where you convert heat in mechanical energy. So you have that expansion in the turbine that causes rotation. And then the mechanical energy goes from there, and that gets converted to a magnetic field to electricity. So there's quite a few processes when you think about the raw material going in, natural gas or coal or whatever, to the output, which should be electricity. So that's one of the advantages. If you actually look at, 33% efficiency, that's not bad. But look at electrical efficiency, 25%. That's really good. That's not the best way to do it. There are much better ways to do conversion from chemical energy to electrical energy. Does anybody know which one is the best? How about a fuel cell? It's hearing some stuff about fuel cells. They've been around for forever. They've been in space stations. They've got that because they actually can create electricity from water and hydrogen, but you can use fuel cells, and those can push 70–80% efficiency. Yes, sir.
Yeah.
Yep. If you have access to hydrogen, which is not easy to find, what I mean by that, you can say, hey, I can go, get some water. There's all kinds of hydrogen there, but you've got to get hydrogen separated from the oxygen. The water going in is not really that good, but you can get 70–80% efficiency with fuel cells. So that's a direct conversion. You're cutting out a couple of processes, so that usually makes things more efficient. But our input power is torque. We've got some stray and mechanical losses. Now we are using our magnetic field, so we are converting everything over. We've got a mechanical system here, and now we're starting to convert things to electrical energy. Then we've got some core losses. We've got some electricity going on here. Now we're going to convert that. Now we actually have electrons flowing into the stator, and then moving out, we have electrical energy. And just notice it's VI cosine theta, not VI, because that would be S, right? That would be the total power, and the total power includes reactive power, which is Q, but that's not real power. So all the energy that is put into the system actually doesn't have to include any energy for reactive power. That comes from another place or another supply. So your turbine is only putting in watts, and you're outputting watts. Okay, that's when we do these power or efficiency calculations. Then we moved into synchronous generators, and again, it's the same basic concept. It's a machine, so it can go either way. And we took our stator that had those 3 windings spaced evenly around the stator, which generated a magnetic field, but we don't have anything inside the stator. So our synchronous generator means we put something inside the stator. And that was a rotor that had windings on it, and you only had a set of windings that would provide DC energy. You need to have DC energy, and the reason why you need to have DC energy is because you need to make sure that that power going in always produces a constant north and south. It doesn't change. It's not rotating on there. It's not inducing a magnetic field. It has to be a fixed north and south. And that is what causes it to be a synchronous machine, because it always is north and south. It never changes its magnitude or its speed. It's fixed at that value. A synchronous generator has to operate at synchronous speed. Okay. So they must run at whatever the number of pole pairs, your electrical frequency divided by the number of pole pairs, that is where it has to operate. If you were to energize this machine and run it at less than 1800, 1200 RPM, it would not output 60 hertz. Okay. That might be okay if you're running freewheeling, meaning you're not connected to the grid. But the moment you connect to the grid is going to tell you will operate at synchronous speed, because the grid has to be at 60 hertz. So interconnecting to the grid, we talked about synchronizing a generator onto the grid. There's a little bit of a process to make sure that that's done correctly, so you don't damage pieces of equipment. So then you have two parts. You have the rotor and the stator. The stator is, because this is a generator, those are induced currents. The currents are induced based on the amount of load that's there, and they're going to apply or cause an applied torque or induced torque that is equivalent to the current that's being drawn out of a machine. On the rotor is fed DC, so I can do two options. I can either have a permanent magnet, which is not a great idea unless you're, really not worried too much about the system, or most likely, at least for a decent sized generator, it's going to have a DC supplied to the rotor circuit. And then that rotor or that DC is what is caused or providing our field current, our DC field current. Remember, we had some hard times with this when we looked at the homework, especially when we looked at the characteristic curves. But what we saw is there's a x-axis, which is a DC current, and the y-axis is either going to be an AC or voltage or an AC current. Okay, don't mix your metaphors. Make sure you understand that you can't divide an AC quantity by a DC quantity and expect to get the real value. Those are completely isolated circuits. In fact, we oftentimes will show the DC over here. No electrical connection whatsoever. Not even a magnetic field that's going over there. When we do that, we can adjust the current over here. And we can increase or decrease that to get more voltage here or less voltage. And increasing or decreasing that field current is how you increase or decrease the amount of reactive power, Q, going in or out of the machine. Assuming that that generator is at a fixed 480 volts, or whatever voltage it is, the terminal voltage, all you can do by monkeying with your field current is change the reactive power. Now, if it's running freewheeling, separate from the grid, that's a different scenario, and that's the operation is a little bit different, but most of the generators you're going to come across are going to be connected to the grid. So all field current adjustments are going to do is change the reactive power. And that means that this magnitude of Q, or EF, I'm sorry, is going to increase or decrease, which means you have magnetic field supplied internally or externally. The inductors don't care. The inductors just need magnetic energy. So they'll either take it from the internal system because you have sufficient excitation, or they'll just steal it from the grid. They're perfectly happy to get it either way. And that's why you can have leading or lagging power factor in a real world synchronous generator. So as electrical engineers, right, we love to model systems because we can't analyze a system with a big hunk of metal and rotating parts and windings. So we come up with an equivalent circuit. And it's a fairly simple equivalent circuit. We need the voltage source. That's going to be the power source. And that's going to be an ideal voltage source. And then we have some leakage reactance, some armature reaction. We have a bunch of different things that will include inside of our circuit. So those are two reactances or two inductors. And then if our coil of winding is sufficient, that it's big enough that you have some reasonable resistance, you're going to get some I squared R losses in there. And how do you determine those? You do open, short circuit, and DC tests. I had a question about that this morning, so I'll pop up this figure. Okay. When you do open circuit tests, you have no load on the generator, and then you just monkey with your field voltage. You can see this is my field voltage, my field current, and this is my field current. This is a DC current. So you're just increasing it, and then you're monitoring the voltage on the terminal. That's all you're doing. Okay, and you come up with a curve. That's the only test that you're doing. You get the generator up to speed, you run it at a synchronous speed. You have to run it at synchronous speed because part of the voltage that is there is determined by the rate of change of the magnetic field. So if your rate of change is lower because your speed is lower, you're not going to get good results. But if we increase the speed to rated speed and we start monkeying with our field current, we can actually measure the terminal voltage and we can get the open circuit characteristic current. Then we turn off the generator, or maybe you could do it at running if you feel comfortable doing this, but then you run a short circuit on the terminals and then you monitor the current and you do the same process. you monkey with the current until you get to approximately rated short circuit current. You can actually go a little bit higher, but you don't want to drive it too much because you will damage the windings. And those are the two curves that you're going to measure. This air gap line is showing you if you did not have any saturation inside the material, then you would have a straight line. So the way that you draw the air gap line is you basically, up until the point that the open circuit characteristic starts to become nonlinear, you just have a straight line. So the air gap line is if the generator did not have any saturation. So that's the unsaturated region or the unsaturated voltage of your generator. Okay. The open circuit characteristic, typically, especially where we're operating at, that's going to be operated in the saturated region because your nominal voltage, you see V rated, is well into the nonlinear or saturated region of the open circuit characteristic. Whereas if I go over here, that's unsaturated, right? Because it's still a straight line. I don't have to worry about any armature stuff or anything that's happening inside the magnetics. That is all linear. So that's just a straight line. So I just continue up, and that's how I can get those values. You'll also notice that the short circuit characteristic is also a straight line. There's no saturation involved with that. So you can use this information, you can glean whatever you want to in terms of, hey, what are the characteristics? So most of the time, if you have an open circuit characteristic, you can get the saturated impedances. If you don't have the open circuit characteristic, you can use the air gap line to get your unsaturated impedances. So if you remember the Northfield Mountain homework where we looked at that, we could actually see the Northfield Mountain told us any point along that unsaturated characteristic or the air gap line would have given you X unsaturated. You could have calculated that. I just focused on, if you remember from the homework, I just showed you those points in the line. I showed you actually on the open circuit characteristic, because many times you don't know what the air gap line is. You have to draw that in. But that literally, again, is you take a straight edge and you draw it in. And that's your air gap line. But you should be able to get any point. If you draw, if I get this point here and this point here, I should be able to draw the short circuit characteristic. So to do the short circuit characteristic curve, I only need a couple points to be able to do it because it's linear about that whole point. To do the open circuit characteristics, I have to do a couple points over here until it starts to become unsaturated. Then I have to do lots and lots of points to actually get realistic results. Okay. To get the air gap line, I don't have to calculate it. I just draw a line from where I'm within the linear portion of the curve. Okay. So that's how you can use this data to go ahead and get the results that you're looking for. But it's a really simple calculation. You can just see it's V divided by I. Make sure this is the armature current and not the field current. Because remember, an AC voltage divided by a DC current does not give you a reactance. I don't know what it gives you, but it doesn't give you a synchronous reactance. And then I did mention something about short circuit ratio. The short circuit ratio is if you know what the rated current is and the rated voltage, you just take those two field values and divide by that. Sometimes you'll actually get that data. You can also do it by just inverting the synchronous reactance. That's another way to do it. So that's the short circuit ratio. Just kind of melded into item number 4. And then a synchronous motor is just a synchronous machine operated with the power going in. So all the stuff that we apply, except now my current direction is going in. So your terminal voltage is going to be fixed. And then you get drops in your system, where the other way, your terminal voltage is fixed, but your drops are from your excitation system out, or your internal armature voltage. So we could use the concept of if it's a synchronous motor or generator, we can tell just by looking at our phasor diagram. We saw that if our terminal voltage, VT, which we pick as a reference, if that's ahead of our EA, then delta is negative, and we have a motor. If EA is above VT, delta is positive, and we have a generator. The magnitude of EA and VT do not tell you if it's a motor or a generator. The only thing about magnitudes of EA and VT, if it tells you if reactive power is going in or out of the machine. And again, the reason being, and we talked about this in an earlier class, but we said that the magnitude of voltages tell us the reactive power flow, and the angles tell us the direction of P, if it's in or out. So if it's a positive delta, that's the angle, and P is out. If it's negative, P is in. If EA magnitude is greater than VT magnitude, it's Q out. If EA magnitude is less than the magnitude of VT, then Q is in. So you can almost, again, exclusively determine what's happening in terms of operation just by looking at a phasor diagram. And we'll see that a lot more when we start looking at transmission line stuff if you take the follow-on class of that. The last thing is, remember, you can't start a synchronous motor across the line. You gotta start a synchronous motor either at a lower frequency. I guess you could start it across the line, but at a much lower frequency. Or if it's like in the case of the Northfield Mountain one, where it's pumping water up from the Connecticut River up to the top of the mountain. The idea there is there's a pony motor to get it to rotate, get it close to synchronous speed. And so once it got close to synchronous speed, then you could energize it and then it would be okay. The other option is you could try and start a synchronous motor with its damper windings, but you don't see that all that often anymore. And then the last one is if there was a way to actually get it physically rotating, right? So that synchronous motor at Northfield Mountain. But another option would be, what if we could actually use the pump to get it to spin? Well, unfortunately, gravity is going to work against you, right? Because the water's here. So you can't ask the pump to pump water up to the top and get it spinning. So that's why it doesn't work in that application where you're a hydroelectric dam. You just can't get it to work. But when we talked about using, what was a good example? If we talked about using a wind turbine, for example, right? We can actually get the wind to get it rotating a little bit, although I guess a wind turbine would be a good application. What would be a good application where we would get something to get it to run as a motor? Maybe if you get a conveyor and somehow you can move the conveyor, if you could get it started to rotate, and then maybe that would be a way to do it. So the mechanical load would actually be a way to do it. It's like somehow if you had a reciprocating engine and you wanted it to actually pump, maybe you could go in both directions where you could either compress fuel or you could decompress fuel. So maybe like a heat pump for your house, that can work in either direction. So maybe something like that, but you don't see a lot of applications like that. So most of the time you'll either see most of the applications, you'll see a motor that gets it up to speed. And like I said, in some cases, you'll actually run the generator with a variable frequency drive to do that, but those are pretty expensive. Whereas a small motor, you can do it for, I mean, it depends on the size of the motor, but 1,000 horsepower motor might cost you 12 grand, 13 grand. You need some complicated mechanical systems to couple those two, but you can make those work. So here's the questions. Voltages and currents in a synchronous machine. So what that tells me is immediately start to draw an equivalent circuit. Calculate power flow in a synchronous machine, which means do those diagrams to show power losses in the machine in either direction. Given test data, find a synchronous machine equivalent circuit parameters. Northfield Mountain example we did, also the one we did in the other homework. But if you're confused, make sure you include those plots, right? The plot we just looked at on slide 20. That will help you with understanding how to get those parameters. Calculate speed of operation. That's basically pole pairs, right? How many pole pairs? So including that, if I divide by the number of pole pairs? Do I multiply by the number of pole pairs, etc.? And then determine magnetic fields given a stator configuration instead of currents. That's how we did all that stuff here, right? Where we had that rotating magnetic field. So being able to use your hands and being able to add things vectorially to get results. So make sure you know how to use your hands and make sure you know how to add things vectorially. And that's what's going to be the exam. So I did cut out one problem because we have the exam on Thursday during class. As per your request, I don't want to see any head nodding. This is a democratic society. So you have to look, you have to point the finger at yourselves. It wasn't me. I was happy to do it yesterday. Most of you were not, but I was happy to do it. So anyway, it's going to be during class. Get an hour and 15 minutes, maybe an hour and 20 if we start a few minutes early. But we really can't go over because there's a class in this room right after. And other people have classes that it's just too difficult. Hey, can you stick around another 20 minutes? It just won't be fair to everybody. So got an hour and 15 minutes. So you're going to have to work, get organized, you know, so be as organized as possible. Because that's the nice thing about doing the exam during the lab is you can actually come in and just sort of, all right, I can take my time and I can do this. This one, you should have plenty of time to do it, but you're going to have to understand that doing test anxiety and do I know the material, it can just cause some problems there. So the normal rule of thumb when you're under a time crunch or a perceived time crunch is start with the problems you know you can do. Get the easy ones that you know think are easy out of the way, and then move to the more complicated ones, because that might actually help you do the more complicated. As you get started on the one that's really tough, and you spend 3/4 of the time working on this one problem, even if you got it right, you still have 5 other problems, and you only have 25% of the time left. So you're just playing the odds of can I make this work? I don't know if you want to do that. Yes, sir.
So we're not covering induction motors on this one?
Nope. It's all going to be synchronous. We'll do induction motors on the next test. So questions?
Any curve stuff?
No. I'll be just looking at curves and looking at the power factor. That's useful if you're trying to figure out operation details. And I provided some information about this as a V curve, but for the most part, you just look at the curve. There's not a lot of useful information to glean on those. Yes, ma'am.
A synchronous machine.
In terms of the calculations for,
Yeah.
okay. Is it a motor or a generator? Right, so that's what I'm saying. Which one do you want? Do you want a motor or a generator? Okay, so if it's a synchronous motor, we know we have armature current going in. We know our terminal voltage is going to be fixed. Let's say it's a Y-connected machine and it's 480 volt. The very first thing you have to do is, this is a 3-phase machine, so the voltage 480 is going to be across 2 lines, but not across the phase. Across the phase, we have 480 divided by square root of 3. So that's the first instance of where we know this has to be dividing it by the square root of 3. We're also needing a reference point. In AC circuits, we need a 0-degree angle. That's our reference point. So we need to go ahead and do that. And so now you know that this is 480 divided by square root of 3 at an angle of 0. That's the reference point. If it's a motor, most likely you're going to know that this is drawing 100 at a 0.8 leading power factor, right? Because if the mechanical engineers are saying, well, the load on this is 2,000 horsepower, that's really useful, but how can I get the power or the current from that? If it's 2,000 horsepower, that's output of the machine, right? If that's a motor. So the first thing I need to know is what's the speed of operation? Is it 1,800 RPM, 1,200 RPM, et cetera, et cetera. Then I need to know the losses inside the machine to be able to calculate that. So you need to know a lot more information. So typically you'd be given something like this. So once you know it's 100 at an angle, at a 0.8 power factor. So now I can draw my power triangle. So this is, actually I can't draw my power triangle. I guess I don't need to draw my power triangle. So I know that this is IA. This is VT, I should say. 480 divided by the square root of 3 at an angle of 0. The current over here, whoops, this is a leading. So the current is 100 at an angle of positive inverse cosine of 0.8. So let me erase that. That gives me my current. So now I can calculate what that angle is. So inverse cosine of 0.8, I think is 36.87. Positive, because it's a leading power factor. At that point, I can say, all right, well, what are, let's see, what would be, we know the current, so what would be EA to make this machine work? So you need to adjust the field current. So EA, you've got voltage drops in that direction. So you just do KVL. So EA is equal to 480 divided by the square root of 3 at an angle of 0, plus, or actually minus, because those are drops, right? So the voltage is decreasing. So minus 100 at an angle of 36.87 times RA plus J XS. And once I have EA, I really only care about the magnitude of EA, because then what I would do is I would go back to this curve over here, and I would say, okay, well, what kind of field current would I need to do? Well, I would need to go and get, this is open circuit, so I'd have to have some sort of a field current that would give me a voltage over here. And then I could kind of estimate what type of a field current I would need. It wouldn't be exact, but it would be pretty close to what I would need, because again, I can't actually get those line losses. And this would be a case where we could actually do a phasor diagram. Where does EA end up on here? Is it above or below? Or can you tell? This is a motor. So does the torque angle need to be positive or negative? Negative. So you know it's going to be down over here someplace. Is it going to have a magnitude that's greater than or less than VT? Less than? Everybody agree with Garrett? Not sure to agree with Garrett.
His leading was.
Careful. So do a power triangle here, right? The power triangle here is going to have a P. Where's Q? Down. So in this motor, P is going in. Where's Q going? It's negative. Got to go out, right? And how do we get Q to go out of the machine? Magnitude of EA has to be greater than VT, doesn't it? That is a hard concept to grasp, because normally when you think, hey, current's going this way, the voltage over here needs to be less than VT, not an AC. The angle will be less. So the angle would be a negative number, but the magnitude will actually be greater. And that's because it's a leading power factor. That's why it's so important to do these power triangles, because if I look at this motor application, P is going in because it's always going in, but because of the negative Q, Q is in the opposite direction of P, that means it's going out. So your actual EA magnitude would be greater than VT. Yes, sir. It depends. It depends on the power factor. Because in a leading power factor for a generator, so let's switch it around to a generator. What's the direction of P? What's the direction of Q if it's the same power factor? Leading power factor. In. Because this power triangle doesn't change, right? Q is in the opposite direction. So if it's a generator, this is VT, and this is EA. So the magnitude's less. That's why power factor really makes things hard, because you can have a leading power factor. Sometimes the magnitude's less, sometimes the magnitude's greater. And it's unfortunate that that's the case, but that's just how the industry does it. We just have leading and lagging. A better way to say it would be over and under excited. Because if it's overexcited, I know Q's going out. I don't care if it's a motor or a generator. Underexcited, I know Q is going in. Doesn't matter if it's a motor or a generator. But the problem is, how many times do I need to know Q, or do I really want to know what I is? Because I is where I can do all my calculations. So actually knowing the correct angle for I is way more useful. Yes, sir.
How would you get EA in this problem? Would you be given a DC current in the chart?
Yeah, you'd be given a plot, remember?
So
You'd actually have to, you'd actually calculate EA from this equation here.
So you'd be given what the equivalent circuit is.
You'd have to know what, or a way to calculate it, right? You'd have to have the equivalent circuit parameters. You'd have to have a curve like this to be able to calculate that. And then you could do it from here. You can get, at least you can get X sub S saturated and unsaturated from this curve, but normally you use the saturated value. So once you have that, if you don't have RA, you can neglect it, but you can get from this curve XS saturated, right? That's not a confident yes.
Okay, so you don't get EA.
Well, you won't get, you get XS from here. You calculate EA using just circuit analysis here. The only reason why I'd go back to the curve is I'm trying to find what nominal field current I need to run the machine at to get that voltage. Okay. Yes, sir.
So for typical generator, the EA is going to be positive.
The angle if for delta is always positive if it's a generator, negative if it's a motor.
Would the IA also still be positive for the leading?
Would IA angle?
Yeah.
No, that's determines if it depends if it's leading or lagging.
If it's leading, positive then?
So the leading or lagging has to do with VT and IA, right?
Yeah.
So it can be positive or negative. It doesn't matter. It can go either one.
Okay.
Doesn't have to be a motor or a generator to be positive or negative. That's just if it's a leading or lagging current.
So like, for the motor, so IA is drawn with a positive angle.
No, this is not because it's a motor. This is because it is a leading power factor.
Okay, that's just leading or lagging that determines.
Correct.
Positive or negative for
Yep.
motor or generator.
Yep. The only thing that determines that current is used for a motor or generator is the direction of current. Is it in or is it out? That's why this stuff is hard, right? Remember we said go back to the fundamentals. If you can understand power triangles and power factors and leading or lagging, it hopefully makes this material a little bit easier to follow. Other questions? Yes, sir. The only way to do that is you'd have to have a bunch of test data.
Yeah.
Well, just use this equation right here, right? So here's your curve. And over here, you have the equations. So if you do have the DC test, you have the ability to calculate RA. Then to solve for X or Z, you would just say, all right, well, here's a saturated value. So here's my voltage. And here's my current. And Z magnitude is V divided by I. That's a saturated value. Unsaturated value, you do something over here. This one and that one. So the only example you can do is you've got to have some test data. And that's what we did the Northfield Mountain one. We had a bunch of test data. We did the calculation that way. So you literally have to be given some plots, some curves to be able to do it. And if you use the air gap line, you're going to calculate unsaturated. So you can use parameters on the air gap line if you have it. If you need to do saturated, you've got to use the open circuit characteristic. So calculate unsaturated, just use the air gap line if you have it. If you need to calculate saturated, you need to use the open circuit characteristic. But literally, it's just looking at points on a curve. So if you have a problem like this, just show the little picture, right? Just show the plot of what you're trying to do. And that's essentially how to tackle this problem. Other questions? Anybody in TV land with questions? All right, well, really quickly, so my availability tomorrow, I should be on campus for most of the day. I do have a sick child. I had to leave early to go pick up a kid from school yesterday because he has conjunctivitis. I don't know if you know what that is, but it's a very contagious eye thing that kids get. So he gets goop in his eyes 4 times a day, and he's not allowed back in school for a minimum of 24 hours or until the redness either goes away or is manageable, because the school won't let him in. He's contagious. So if for some reason he's not allowed to go to school tomorrow, then I might not be able to be in, but I'll be available on Zoom. You can send me emails. I'll check things periodically. It just changes things a little bit. I apologize, but this was just, I was here yesterday and I got a call at, I don't know, 12 o'clock, whatever. And so I had to go pick up, you don't have a choice. It's like, come pick him up. You don't ask, they tell you. So, and it's not because he's ill, it's just because it's so contagious. I guess it's so contagious that you don't want other kids to get it. So I apologize in advance if I'm unavailable physically tomorrow. My plan is to be here. I should be here by no later than 7:30-ish. Again, it just depends on how the morning goes and if he's still having symptoms. Unless anybody here wants to volunteer to take care of a kid with red puppy eyes. 100 on the test. All right. There's nothing else. Have a great day and hopefully see you tomorrow. Take care, everyone.